Yes.
Yeah.
So again, I welcome Dr. Pandey. So Professor Pandey is currently working as a Deputy Dean Research and Sustainability at Research Center for Nanomaterial and Energy Technology, School of Engineering and Technology, Sunway University, Malaysia. His current research focus is on advanced energy materials, thermal energy storage, nanomaterials, and its application renewable and sustainable energy technologies. He is listed in top 2% scientists in the world by Stanford University. He is recipient of Sunway University's Excellence in Enterprise and Innovation Award 2023 and Sunway University's Excellence in Research Award 2022. Besides, he is recipient of several international and national fellowships. Professor Pandey is an associate editor and editorial board member of several ISI and Scopus journals. He has published more than 300 research papers as per Scopus database, filed 7 patents on different renewable energy technologies, as well as he has edited 3 books published by Springer and elsewhere. He has over 10,000 more citations with H index of 52 as per Google Scholar database. I welcome you, sir, in this ATAL online 6 days faculty development program on clean energy and environment sustainability. Good evening, sir.
Good evening, Dr. Abhishek. First of all, thank you very much for inviting me for this ATAL FDP talk, and I really am honored for this invitation, and I'm happy to be here. So let me first share the screen.
Yes, Dr. Mulli, please make co-host.
Yes,
to
sir.
Pandey,
Yes, sir. You can share your screen, sir.
Okay.
Then you can share your screen.
Okay. So can you see my slides?
No, sir. Currently.
Yes, sir.
Yes, sir.
Yes, sir.
Can?
Yes, sir.
Okay. So let me double confirm. You can see my slides, right?
Yes, sir.
Yes, sir.
And
Is it
I'm
possible
audible.
to make it full screen, sir? Yes, sir. Audible, sir.
Yeah. So I have made it full screen. Is it full screen?
Yes, sir. Yes, sir.
Okay. So thank you, Dr. Abhishek, and I'm really honored to be here. And to start with okay, so today I'm going to talk on the solar energy collectors combined with the phase change materials for sustainable energy supply. And thank you very much for introduction. As you know, I'm Adarsh, and I'm Deputy Dean for Research and Sustainability in the School of Engineering and Technology, Sunway University. So before I start the talk, I'll give you some of the glimpse about the university. Okay, not too much, a very brief glimpse. Okay, so as far as Sunway University is concerned, Sunway University is basically a pretty young university. However, within this very young span of time, university is ranked top 500 university as per the THE ranking. And as per QS ranking, we are 539 ranked university in the world. And everyone say that, okay, we have a campus, and we say that we have the city. So the picture what you can see right now here is basically Sunway City. Can you mute?
Yes, sir. I'm doing it.
Someone is seems like. Maybe what you can do, you can mute everyone, and when there will be a questions, they can
Yes, sir.
open. Okay. So basically, we have a campus here, and in the campus, you can see that it's not only the university, but the university has university has the university campus, and within the campus we have a Sunway College, as well as the Sunway International Schools, and the hotels and malls. This is a theme park. which is owned by the Sunway itself, Sunway Group itself. So we have not only the campus, we have the Sunway city, whole city. Within the Sunway University, in the surrounding, you can find out all those things in the university. So as far as Sunway University is concerned, we focus a lot on the collaboration aspects, and Sunway University has we are collaborating with almost all the top universities in the world, and we are a research intensive university, research focused university, and that's the reason you can see that we are basically here in Malaysia, and we have collaboration with Harvard University, Lancaster University, UK. Lancaster University is our education partner, basically. Education partner means that the students enrolled with us, they get the dual degree, or degree by Sunway University, another degree by the Lancaster University, UK. We have pretty much good collaboration with University of Cambridge. In fact, within the campus of Cambridge, if you go, you'll find out that in the name of our chancellor owner, there is a building, medical center over there within the campus of University of Cambridge, University of Oxford, and we are working with MIT as well on carbon dioxide capture and utilization. So yes, and you can see left hand side we have almost 20 research centers within the Sunway University. So you can understand that these research centers are only focused on the research aspects. They do not kind of not involved much in the teaching. Their core business is just to do the research. So I myself basically work in one of the research center. My research basically housed in Research Center for Nanomaterials and Energy Technology, and we have different research centers which focus on the different sustainable development goals. We focus a lot on the accessibility, sustainable development goals, and planetary health. And as you can see that these are different such research centers such as carbon dioxide capture and utilization, research center for crystalline materials, research center for nanomaterials, human machine collaboration. So we have so many research centers here. As far as Sunway Group is concerned, Sunway Group is having the 13 different business units. Sunway Group is in the real estate, healthcare, leisure, digital, malls, education, hospitality, so many different areas. Basically, Sunway Group works. So Sunway University is a part of Sunway Education Group. So as I told you, I work in School of Engineering and Technology. Within that, my research basically is in this lab, and these are some of the pictorial view of the lab, where what we have done this lab, Research Center for Nanomaterials and Energy Technology. Here in one of this area, this is called the synthesis or wet chemistry area, where we synthesize our nanomaterials for energy applications, or we come out with the new composites, especially focusing on the energy applications. So after synthesis is done, we characterize them in this room where we have a hello. Dr. Abhishek, just to confirm, am I audible?
Yes, sir. Yes, sir. Yes, sir. Audible, sir.
Yeah. So maybe in between, in every 15-20 minutes, I'll just confirm that.
Sure, sir.
Sure. So in this characterization room, we have differential scanning calorimeter, we have TGA, we have FTIR, we have SEM, we have UV-vis for the characterization instruments. And another room of the lab is basically where we do all sorts of kind of application things, where we have a solar simulator, cycle tester, conductivity measurement, and different other types of setups, basically customized setups in this area of the lab we have. So this is one of the research centers lab where I work. These are some of the other pictorial view of the lab. Okay, so that was a very quick introduction about the university and the research center. So let's come back to the topic. So before I start on the phase change materials and the solar collectors and all those things. Let's understand the sustainability aspect. What are the sustainable energies? Okay. So when we talk about the in general sustainability, concept of sustainability is that we are doing anything so that we can meet the needs of present, needs of our own without compromising with the ability of future generation. Okay. So we can fulfill our need without compromising with the future generation's need. Okay. So and if any kind of energy which fulfills the definition, this definition is known as the sustainable energy. So what are those energies? Are the fossil fuels are sustainable energy? No. Why? Because they do not fit into this definition. How? If you talk about the fossil fuels such as the coal, okay, how coal doesn't fit into this definition, let's understand. Okay, so the coal basically is fossil fuel. If you are using the coal, which we are basically using coal, oil and gas fossil fuels, still we are using more than 60% roughly uh, in overall world scenario if you see. Okay, so the thing is that the coal is limited, oil is limited, and the way we are using, if in the same way, if we are going to use in the same pattern, if we are going to use the coal, oil or gas, they will deplete in the future. So you forget about this is the first thing. So it is not renewable. Okay. So maybe what it can do, it can fulfill your present need, but the problem is that for your future generation, there won't be a coal, oil, or gas if you are using that for this. So it doesn't qualify for the sustainability. Okay. Second thing, fossil fuel, you know that they emit the CFCs. They emit the CO2. Okay. So they emit these greenhouse gases. So when they emit the greenhouse gases to the environment, it means they are polluting the environment. So when they are polluting the environment, what is happening? We are compromising with the our health, not only our health, but also the future generations' health. So when we talk about the fossil fuels, yes, of course, they have the potential to fulfill your need in the present. But when you are using for the present, but you are compromising with the future generation as well as your present health. So they do not qualify for the sustainable energy. When we talk about the renewable energy such as solar energy, wind energy, biomass energy, so they qualify for this definition. They qualify to be sustainable, such as solar energy, which I'm going to talk about today. So solar energy, if you talk about the solar energy is energy which has a lot of potential. We will understand in the next slide. Okay, they can be renewed at a significant rate. Okay, until and unless the sun is there, you can get the solar energy. It's a matter of only harnessing that amount of energy which is reaching to the sun. Second thing, when you are harnessing that energy, it is not polluting the environment. So you can harness as much as whatever it is available. And second thing, it is not polluting the environment. So it is a sustainable energy. So that's the definition of sustainable energy. So let's see this diagram. If you see this diagram over the year, which is showing from 1800 to 2022. Okay, over the year, if you see the pattern, you will find out the pattern. Initially, we were dependent only on the traditional biomass, if you see. Okay, mostly our energy needs were catered by traditional biomass, and energy requirement was less. There are different reasons for that. First thing, population was less, whatever it is now. Second thing, there were no industrialization. So most of the energy needs were only for the cooking, basically, okay, or some sort of heating using the biomass, traditional biomass. So the energy requirement was less. But over the period of time, if you see, coal came into the picture and the electricity generation came into the picture. Okay, so here we had energy requirement for the cooking or lighting, especially using the fire. Okay, but over the period of time, inventions took place, and we invented the electricity. The so we started using the coal, and coal was the primary source of energy. Still started taking place from around 1900s onwards. Okay, so and if you see in the current era, still, if you see this picture, you'll find out that we are still dependent on the traditional biomass, coal or oil, mostly, if you see, okay, natural gas. But from, if you see this picture, you'll find out that from especially 19, around, if you see it around 2000, you can say that, okay, from here or a little earlier than 2000, this renewable energy especially started taking the momentum. So currently the share of electricity by the renewable energy is higher, but not higher than the fossil fuels. So that is what the target of the especially these sustainable development goals. This energy is one aspect, which especially goal number, if you talk about the goal number 7, clean and affordable energy, and goal number 13, which talks about the environment. Okay, so these two goals talk about these type of energies, means they advocate for the energy which is clean, which is sustainable in nature, which can suffice your needs, which do not compromise with the future generation, basically. Okay, so so that's why that's the reason, if you talk about energy consumption, basically is continuously increasing, and still this is on higher side. Okay, and there are different sectors which basically have the higher amount of energy consumption, such as the buildings. Building consumes 1/3 of the global energy and continue to contribute significantly to the carbon footprint. And that's the reason, okay, we need kind of a sustainable energy, sustainable energy, first of all. And now, but the problem is with these sustainable energy, especially the renewable energies, and especially if you talk about the solar energy, the problem with this is it is available only in the daytime. It's not available in the night time, or even in the daytime when it is available, it is not available, it is not consistent throughout the day, right? So solar energy is basically, if you talk about the Indian scenario, you'll find out that the average solar radiation for India, it is roughly around 5.5 hours throughout the year. Means average solar radiation is 5.5 hour, and we have 24 hours of cycle. So we do not have solar energy for rest of 18.5 hours. So we are advocating a lot about such type of energy, but the problem with this energy is that it is not consistent. It is not available throughout. In contrast, if you talk about the fossil fuels, once the fossil fuels, you have that supply, you can harness that, you can produce the energy from that energy, from that source, basically throughout the 24/7. But this energy, especially solar energy, when we are talking about, it is not sustainable in the nature when we talk about the sustainable supply. Okay, so what is the thing what we can do, basically? What we can do, so we need kind of a sustainable energy storage. We need, when this energy is available, when solar energy is available, we need to have a mechanism where we can store the energy. And you know that it's a well-known mechanism how to store the energy, solar energy. The one of the most prominent way of storing that energy is using the electrochemical batteries, like lead acid batteries, lithium-ion batteries, and all these batteries. So you can store the electrical energy through the batteries. But the problem is that, but the thing is that why we need the thermal energy storage? Why not the electrochemical energy storage? The justification for the thermal energy storage is that when you are going for the electrochemical energy storage, it means that you are storing the energy in a highest grade. And when you need the energy for the low grade energy, suppose you have to heat the water, okay, okay, you have to cool the room, okay. So basically what you are doing, you are converting the highest grade of energy to the low grade energy, and then you are utilizing, and there are a lot of losses during this basically uh, conversion. So we have kind of a energy storage. We are using thermal energy storage. We have variety of range. Utilizing those range, the kind of temperature you need. If we need like 20 degree centigrade of temperature, you need 30 degree, you need 40 degree. So you have kind of a materials which can basically give you energy at that particular temperature. So that's why thermal energy storage is kind of one of the one of the efficient way of storing the energy. We'll discuss more about it. Okay. So let's understand here what is the roughly what is the energy demand. Okay, in the projected world's energy demand would reach up to roughly around 30 terawatt in 2050. And if you talk about the current energy demand is roughly around 18 terawatt of energy. So if you see here, from here to here, we would be needing roughly around 10 to 12 terawatt of more energy by 2050. Why? Because if you talk about the West, if you talk about those continents like Europe, US, these continents are now a developed nation. What does it mean? I have looked through the data, energy consumption pattern data, and I found that, okay, these continents, they have almost consistent from last 10 years, the energy demand is almost same. It's not increasing. Why it's not increasing? The kind of development, industrialization should be taken. It has already been taken. So energy demand and population is not increasing that much. But when you talk about the Asian continent, I found that in Asia, what is happening, the energy demand is increasing. Still, we are still increasing. Why? Population is increasing, industrialization taking place. So it is expected that world's energy demand would still increase by more than 10 terawatt by 2050. So the thing is that when we are harnessing, if we keep on harnessing the fossil fuels, the problem with that is that that won't be available after 80 years or 100 years of time. So you need to find out the solution. You need to focus a lot on these renewable energies and other technologies which can support renewable energies, such as the energy storage technologies. So these are the carbon neutral energy sources. Okay. So, okay. I always say that, okay, don't go for like one kind of a technology and fulfill all of our need. I'm not saying that just go for the solar energy, but I'll give you one data which I have taken one of the study from the Harvard University. Okay. So as per the calculation, if you see the potential of solar is roughly around 1.2 times 10 to power 5 terawatt at Earth's surface. Practically, how much we can harness solar energy? Roughly around 800 terawatt of energy we can harness practically. This amount of energy we can harness. This amount of solar energy we can harness. And what is our demand, current demand? Roughly around 18 terawatt of energy. Even by 2050, it would be not more than 30 terawatt. And practically, we can harness 800 terawatt of energy. And you know that solar energy can be harnessed using two different technologies: solar thermal, solar photovoltaic. Okay. So when solar thermal and solar photovoltaic, okay, out of that, if we take only one calculation, one technology, which is solar photovoltaic, which is more common, you see those panels on the roof, in the buildings or solar farms. Basically, you see the solar photovoltaic panels. Okay. If solar photovoltaic panel efficiency is only 10%, though in the market now we have more than 20% efficient solar panels are available. And if we cover the overall land, 0.61% of the land. However, if the efficiency is 20%, the land area will be less, half. So still we can harness 20 terawatt of energy, only utilizing photovoltaic panels, having only 10% of efficiency. So that is, and second thing, these panels are kind of a modular in nature. You can take these panels anywhere. You can either create a small device or you can go for a big megawatt scales of the solar farms. So solar energy is sufficient. It can actually deliver what you need. It can fulfill your demand in terms of the availability, whatever the energy requirement of the world's there. And second thing, it doesn't pollute the environment. So yes, these energies we need to focus a lot. Yes, as in the previous slide I told you, okay, but this energy is available for 5-6 hours of time in Indian scenario. So we need to find out the solution where, when it is available, when it is most available, we store that energy and we utilize that energy. So Dr. Abhishek, I think it is audible, right?
Yes, sir. Audible, sir.
Okay, great. So yeah, this one I have already discussed. What is the need of energy storage? Okay, so I'm not going for that. So now let's understand why thermal energy storage. I think this one also, but let me give a glimpse of that. Okay, thermal energy storage are having of different types you can store. Okay, but I'll focus more on the phase change materials, which is the latent heat energy storage. And why thermal energy storage? Because no other means of energy storage is so diverse in terms of providing both high grade as well as low grade energy at the end utility. So that's why we need thermal energy storage. Means the amount of the kind of energy you need. Suppose you have to heat the water, you need suppose 40 degrees centigrade. So if you are having the energy stored in the battery, what would you do? Means it is stored in the form of electricity. You will utilize the electricity and you will start your geyser and then you will get the warm water out of it. However, if it is a thermal energy, so what you need to do, you need to having the material which is having the melting point as 40 or 41, 42, and that material can deliver you that amount of energy. So that is why thermal energy is kind of a very diverse in terms of providing both high grade. High grade means it can go more than 1000 degrees centigrade using the molten salts. Low grade means it can go to the sub-zero degree as well. Not only, so you need the energy at minus, you need the energy at 1000. It has variety of options available. Okay, now, so and this latent heat energy storage is basically available in the form of phase change materials. And what are phase change materials? Let's understand how they operate, okay, how they work, okay. So phase change materials are the materials which changes its phase at particular temperature, okay. So that particular temperature is known as the melting point. So phase change materials is very easy to understand. Let me give you one basic example. If you take water, okay, so water freezes, suppose at 0, okay. So what it does, freezes means it is when it is a water, it is in the liquid state. It freezes at 0 means it becomes the solid. When again you increase the temperature, what happens? It goes from solid to the liquid state. When goes to the water state again. So water is also a phase change material. So in many places, water's means ice slurry is also being used to give the cool energy in the buildings. Okay, so phase change materials, what happens, how it works? Any kind of a material, if you take water or you take calcium chloride hexahydrate or you take any kind of a paraffin waxes available in different temperature ranges. Okay, so what it happens, as the temperature rises, it melts, it absorbs the heat energy. Okay, And I mean, it goes from solid to the liquid state. Okay, as the temperature falls, what happens again from the liquid state? It goes to the solid state, and while going from liquid to the solid state, again, what it becomes like it releases the energy. So here it stores the energy when it goes from the solid to liquid state. Again, back from liquid to the solid state, when it goes, it releases the energy. So here you store the energy, and here you means you utilize the energy, that energy. And it could be of different temperature range. It may be in the temperature range of 20, it may be range of sub-0 degrees centigrade, or it may be in the range of, suppose, paraffin bags of 58 degrees centigrade. So it depends. Okay. So as it works basically, so this is known as the charging. When it goes from solid to liquid state here, and you increase the temperature, so it start melting. Okay, it absorbs the energy. So this is a charging. Just like the electrochemical batteries, you give the current and you charge. So here, what you give the basically kind of a temperature, so that it goes from solid to liquid state. Okay, and here it stores the sensible heat liquid, and then sensible heat energy storage is here. And when again it goes back from solid liquid to the solid state, it releases the energy, and that is how energy is being stored and released in the solid using the phase change materials. And these phase change materials are known as the latent heat energy storage materials, or they are also known as the thermal batteries. Why? Because it has the same function as of the battery. So that is also known as the thermal battery. So these phase change materials are available in different varieties. They are basically available in solid, liquid, and in the solid gas. I mean, if you categorize in terms of the phases, solid to gas, solid to liquid, solid to solid, and if you categorize in the form of in the nature, they are available in the organic, inorganic, and eutectic form. So they can be categorized in different ways. Okay, so the eutectic is nothing but the combination of any two of the phase change materials. If you take two organic phase change materials, you combine them, you come out with the composite of two organic phase change materials, it becomes eutectic. And you can combine two of the inorganic, it becomes eutectic. Or you combine one organic and one inorganic, it becomes eutectic. Means mixture of two, any two organic, two inorganic, or one organic, one inorganic. That is known as the eutectic. Why it is important? Because what happens, sometimes the exact temperature range may not be available. So when you combine these two materials, what you can do, you can tune the properties. You can tune the melting temperature. So suppose desired melting temperature is 23. At 23, any material is not available. You can go for the eutectic phase change materials. You can combine. I mean, there is a formula to do that. There is a way to do that. You can follow that way, and you can come out with the eutectic, and you can tune the melting point of the phase change materials to get the temperature what you need. So, but these phase change materials are having some of the issues as well. What are the issues? These phase change materials, when they are available in different ways, they are having the low thermophysical properties. Low thermophysical properties means what? Means they are less conductive. Means thermoconductivity is low, and latent heat also sometimes not that high. Okay, so how to improve these properties? There are different ways of doing it. They have different issues, and I'm going to talk especially about the supercooling and the thermoconductivity. Okay, because better thermoconductivity is one of the desirable property, because if the conductivity is good, it means the PCM will charge faster, how will discharge also fast. Okay. So you need to not having like very high thermoconductivity or very low conductivity. So you need to basically tune the thermoconductivity. You need to tune the melting temperature. You need to um, work on the degree of supercooling. Supercooling is nothing but supercooling is at what temperature it should melt down. It doesn't melt and goes below that point. That is known as the supercooling. So one way of coming out with this issue is utilizing the nanomaterials. And nanomaterials are basically why they are useful, because nanomaterials, you know that definition of nanomaterials. Definition of nanomaterial is when the dimension of the nanomaterial is between 1 nanometer to 100 nanometers. Means they are so tiny, but their surface area is basically high. When you infuse these nanomaterials into the matrix of phase-change materials, what happens? The surface area basically increase, and they might be having the better thermoconductivity. It depends on what kind of nanomaterials you are using. So, which I'll show you some of my results, what we have done it, okay, utilizing the different nanomaterials. So these nanomaterials may be available in different, maybe organic, inorganic, or eutectic, or they might be classified in different way: 0 dimension, 1 dimension, 2 dimension, and 3 dimensional nanomaterials. And in my lab, we have worked starting from 0 dimension to 3 dimensional nanomaterials, and we infused into the phase change materials, and I'll show you some of the results out of it later on. So as far as nano enhanced phase change materials are concerned, these phase change materials, basically people have started working in around 90s, and they started looking towards the carbon nanotubes, okay, with the phase change materials, and they further improved, and they doped the multi-wall, double-wall CNTs into the organic phase change materials, okay. Later on, different types of nanomaterials has been explored during this more than almost 124 years of time, and people have explored metallic type of nanoparticles. People have explored the carbon types of nanoparticles, but there are pros and cons of both nanomaterials. And recently, if you see in 2023, we have first time we have explored, my lab, we have explored tetrapod dispersed organic phase change materials. This is one of first reported kind of a study where we have utilized these tetrapods, and because of its arms structure, they were able to improve not only the thermoconductivity, but they were able to improve the latent heat further, and that is one of the issue. Actually, when you utilize these nanomaterials, the problem is that they can enhance the thermoconductivity, but they can reduce the latent heat. Why? And they reduce, basically, suppose there is a 1 gram of phase change materials, or suppose 100 gram of phase change material is there, and even if you are using 1% of nanomaterials, 1% means 1 gram out of 100 gram, you are utilizing the nanomaterials. So you have PCM left with only how much? 99 gram. So 1 gram you are putting in the nanomaterials. So what it will do, it will improve the conductivity, but the problem is that because of that, it may decrease the latent heat capacity of the, but because of its different shapes and the conductivity and other things, we didn't compromise with the latent heat, as well as the significant amount of thermoconductivity was improved. So as far as footprints of phase change materials are concerned, these phase change materials can be utilized in for different applications. They can be applied for the solar thermal systems, such as cooking and solar thermal power plants, and they can be combined in the photovoltaic thermal systems, and they can be combined with the BTMS. BTMS means battery thermal management system. Utilizing the phase change materials, you can come out with the, because BTMS, what to do PCM in the BTMS? What it can do, basically, the batteries, you know, that having the thermal runaway issue means if you have the high discharge, in charging is not an issue. When it discharges, okay, and rate of discharge is high. If you go from 1C to 3C, means you are discharging the battery faster, more than what it should be. So the possibility of being the battery get heated becomes more, and there can occur a lot of issues of the thermal runaway in the battery. And if you are integrated such type of battery in the EVs, electric vehicles, you might have seen a lot of issues when, in fact, the scooty or the this is available, and you will see that started burning. Electric vehicle started burning. Why? It is basically because of the batteries. So these PCMs can be utilized basically to control, to manage the temperature. So these PCM not only can be utilized in this solar thermal, solar photovoltaic thermal system, but also it can be utilized for the building applications. So building applications for building cooling, building heating as well, not only the cooling. So I'll show you some of our results also of these applications, not all, maybe some of the applications I'll show you. So there are some interesting ideas also apart from these conventional applications of phase change materials. So you can apply these phase change materials to the mattress as well. And if you are applying the PCMs in the mattress, what would happen? It can maintain the temperature basically in the summertime. You might not be needing the direct air con, and the mattress itself would be sufficient for you to control or manage your body temperature. So that is one of the way of using the phase change materials. Or recently, what we have done, we came out with the application of these phase change materials into the jackets, and we tested this jacket to the basically the workers. We patented also this technology, and where we were able to manage a, I mean, significant amount of time of the body temperature basically control. So because as per one of the nature study, we found that, okay, if these laborers, especially the workers who are working in the summer conditions, outdoor conditions, so because of the body temperature goes up, their work efficiency goes down, as well as there are a lot of health issues. So utilizing these such type of innovations can come out utilizing the phase change materials basically. So, okay, but these phase change materials, when we are choosing these phase change materials, what are the properties we should look into? So, I always start with the economic properties. I always say that any technology is viable when it is economical. If it is not economical, it is very difficult to get into the market. Okay, even the technology is very good, but if it is not economical, it won't get its due. If you talk about the solar energy, solar cells, you go back 20 years back. In fact, when I started my career working on the solar cells, so at that time people used to say that, okay, solar energy is not feasible, the cost is very high over the period of time, but people have, scientists have worked a lot, and they improved the efficiency, made it economical. Now you can see these solar panels are basically installed a lot in the Indian scenario, if you talk about. So same PCMs, you need to consider whether, first of all, they are abundant or not in the nature, they are available. If they are not available, it doesn't matter like how much the property is there. So you won't get that material. So what is the need? It is available. It is cost effective or not. Second property is thermal properties, which I was talking about. Suitable phase transition temperature is the one which we should look into the first after the economical properties. So if we do not have suitable phase transition temperature, if we do not consider that, what may happen? your overall application, will be fail. Suppose, take the example, if you have to heat the water, suppose you need the temperature, suppose between 38 to 40 degrees centigrade. And if you choose the phase change material, which is having the, you take A25, suppose, okay? You take the phase change materials, which is having melting temperature 25, and you integrate that phase change materials into the, for water heating. What will happen? The phase change materials will change its phase at 25 and will give you the same amount of temperature, the same temperature range of energy, means 25 degrees centigrade, but you need the water at 40. You won't get the 40 degrees centigrade water. So you need to first look into the suitable phase transition temperature, what application you are looking into. Okay. Then high latent heat of transition. If latent heat of transition is good, means more amount of energy you have. Q equal to mass in m into L, means energy is equal to mass times latent heat. So latent mass times latent heat. If latent heat is good, the overall amount of energy you will get more. Then good heat transfer, which I was discussing. The heat transfer means conductivity should be high. If conductivity is not good, your PCM will take more time to charge, and then also in the discharge. So you need to having these thermal properties. The same, now you should be having the physical properties good and chemical properties you need to look into. Okay. So I mean, I already discussed this in the previous, so I'll just skip this one. Okay, so now let's talk about what I have done, okay, on phase change materials or nano enhanced phase change materials or their applications. Okay, so in this is one of the study I was explaining when I was explaining basically the history of nano enhanced phase change materials, which is published in 2023 in Chemical Engineering Journal, which is one of the top journal, and what we have done, we have used this unique structured tetrapods. We synthesized and we enhanced. We found that thermoconductivity was enhanced up to 94 or 95% using the Genome tetrapods, and there was a significant top up in thermal properties with no decline of latent heat storage. That is one of the important parameters, that you are enhancing the conductivity without compromising with the latent heat storage. Means storage capacity remains the same or top up without compromising with the conductivity. Compromising with the latent heat, your conductivity improves. Okay, as well as thermal conductance and broaden the photo absorbance for tetrapods disturbed thermal batteries. So means what will happen, especially for solar energy application, you need the more absorbance. Okay, so using this, for what we found that when we infuse the tetrapods to the this organic phase change materials, the absorbance also enhanced. It means that the solar energy which is hitting to the material, it will be more absorbed in the nano enhanced phase change materials. So there was another study what we have done. That's a 3D type of nanomaterials we explored. Then we explored the 2D materials utilizing this silver. Okay, and in this study also what we have done, we found that okay, the further utilizing the silver nanoparticles to the phase change materials, means 2D type of nanomaterials. Maybe I'll give you overall comparative what is based on dimension later on. Okay, so here further the thing is that what we improved the thermal properties as well as chemical and thermal stability. That is one of the important parameters. Because you are infusing one of the material to the another material, so it should be chemically stable. So it was chemically stable. Second thing, it should be thermally stable also. Why it is important to have the thermally stable? Suppose any PCM or nano PCM you are coming out with, and it's suppose melting temperature is 50, and suppose it start degrading at 50 or 51 degrees centigrade. So, and you are going for an application where temperature range is supposed between 50 to 60 degrees centigrade. What will happen as the temperature is going more than 50 degrees centigrade? It will start decreasing. It will start losing the material. It will start dispersing. So you need to having the a better thermal stability of the nanomaterials as well, apart from the thermophysical properties. Okay, so we utilized, and then uh, what we came out with the eutectic study as well, as I was explaining. So we did the experimental evaluation of binary and ternary eutectic. Means binary means utilizing the two Christian materials. Ternary means you are utilizing three and four types of Christian materials into together. So ternary means three. Okay, so we have done 21 combination of these, and we calculated, and out of that, based on our applications, we were looking basically between 20 to 25 degrees centigrades. 7 of them we chose. We did the calculation, and based on that, we further experimentally studied, and we were able to reduce the supercool degree of supercooling by 49% without nucleating it, without utilizing any nanomaterials. Means that is one of the another beauty of it. You don't need sometimes the nanomaterials to uh, improve the degree of supercooling and improve the thermophysical properties, but you can utilize two different types of phase change materials, and you can further improve these properties. So yes, basically we targeted here only the salt hydrates, different types of salt hydrates, 21 different combinations we have studied, and this is what we were able to achieve in this study. And then what we have done this study on the because we were looking into the more sustainable options. So nanomaterials which were like readily either available, or the kind of a nanomaterials which were basically I mean, it's a energy intensive sometimes synthesis process. Okay, when we go for 3D, 2D, and all, sometimes in nano scales. So, but what we have done, we started looking into the waste and converted the waste into the nanoparticles, or you not exactly the nanoparticles, but we stopped at micro scale. Uh, the size was roughly around 400 to 500 nanometers. So you can say that microparticles. So what we have done, we have taken the coconut shell, and we have converted coconut shell into the microparticles or nanoparticles, and we utilize those.
Sorry.
We utilize those microparticle and nanoparticle into the eutectic Precision materials. Okay, and we found that okay, we were able to improve the thermoconductivity basically by 54%, which is a very good amount of percentage enhancement. When we talk about the bio-eco-friendly coconut shell, uh, less energy intensive, and utilizing converting the waste into energy, waste to energy applications. So that is what we were able to do. And then we actually explored this coconut shell for different nanoparticles, and we published this one. So one of the another two-dimensional nanomaterials we were trying, which is known as the magazine, which was basically discovered by Professor Yuri Gogossi and the group in 2011. And this material is excellent in conductivity, but the thermal conductivity is not that high. And we tested with one of the eutectic salt hydrate phase change materials. However, this is for one particular eutectic salt hydrate phase change materials. So it can be further actually investigated for other phase change materials. And what happens with the magazine? What we found that, so optical observance basically was improved a lot more than 700%, and transmissibility was dropped by 86%, and the enthalpy was improved. Degree of superkilling was improved. So, but as far as the thermoconductivity, the results were not that encouraging, which we were expecting. So yes, electrical conductivity is very good. The thermoconductivity may not be that good, especially for this type of material. But yes, as I said, that it's a matter of further investigation for the other phase-change materials. Okay. So, okay, Dr. Abhishek.
Yes, sir.
Okay. So I'll take a break of 5 minutes, then we'll start again.
Sure, sir. Sure, sir.
I'll take a water break.
Yes.
Hi, Dr. Abhishek.
Yes, sir. Welcome, sir.
Okay, we'll start again.
Yes, sir.
Okay, sir.
Okay, so I hope you can see my slides.
Yes, visible, sir.
Okay, good.
Yes, sir.
So
Visible, sir.
let's start again. Okay, so this nano enhanced fashion materials, we not only studied the eutectic, not only studied the single nanoparticles, but also what we have done, we have done the study on the combination of these two, means hybrid of nanoparticles. So we have done the hybrid of HBN nanoparticles and also the graphene nanoparticles. Okay, so binary basically kind of a nanoparticles, we have done this study, and boron nitrate we have added with the study of we have done this study with the lauric acid. Okay, and we have added 3% of HBN and 2% of graphene nanoparticles, and the thermal conductivity was enhanced by 97% by utilizing this. Okay, and further the uh, absorbance was enhanced. And this, what we have done, we have done the application with the this I will explain actually later. Here you might not get this point basically. Let me explain in the next slide, then you will understand. Okay, so these hybrid of 1D and 2D also we basically conducted a study with the electronic cooling and the heat sink basically. We applied experimentally the our developed hybrid nanoparticle enhanced lauric acid based phase change materials to the thermoelectric generator and heat sink. And the right hand side you can see the difference. And this is empty heat sink. Over the period of time you can see that how the temperature goes up, and in 180 second of time the temperature goes roughly around 68 degrees centigrade. But when we used phase change materials into the heat sinks, we found that the temperature was reduced roughly around 10 degrees centigrade, means roughly around 58, from 68 to 58. However, when we used our developed nano-phase materials to the heat sinks, we found that the temperature, there was a further reduction in the temperature, which reduced roughly around another below, it goes below around 50 degrees centigrade of temperature. I means when so that is one of the I means if you see from around 70 or 68, it can go around 50 degrees centigrade when you are using the enhanced facing materials to the heat sinks. Means a temperature reduction of around 18 degrees centigrade is a quite huge, and it can basically mm, basically control the temperature. It can manage the temperature of the heat sinks. So we have done these polyethylene based paraffin wax nano enhanced facial materials, which I'll go quickly. Okay, so but in this study, what we have done here further, latent heat was enhanced by 8%, because polyethylene is one of the best conductivity material we have, and these results I won't show. But here I would like to show you this result. So this result is important. Why? When you come out with the nano enhanced phase change materials, nano enhanced phase change material means you are infusing the nanoparticle to the phase change materials for any application. You are going for the application, means you are coming out with a new thermal battery and you are going for the application. You are going to encapsulate with any application, suppose for electronic cooling, building cooling, or you are utilizing with the solar thermal collectors. So how long it is going to work, it is very important to know. Such as batteries, when you go to the market, you look into what is the warranty of the battery. Warranty of the battery means what? You basically want to know that how long the battery is going to work. If the warranty of battery is suppose 1 year, it means that it has the cycle of 365. Means one time you charge, one time discharge, it is called one cycle. Means in a day, if you are charging and discharging one time, it means one cycle. The same way, the nano PCMs means PCMs. You need to find out what is the cycle. One charge and one discharge is equal to one cycle. So we have done experimental evaluation of our this nano PCM, and we did the 3000 cycles of this nano PCM. And after 3000 cycles, latent heat capacity we were especially focusing on. It was initially 0 cycle, it was 166 joule per gram, and it was roughly around 150 joule per gram even after 3000 cycles. But if you see, only paraffin wax at 0, it was 153, and after 3000 cycle, it was 143. But if you compare this with this, you will find out that even after 3000 cycles, the latent heat capacity is roughly comparable to the latent heat capacity of the paraffin wax at 0 cycle. So which is one of the very good result with this. That means if you are integrating this thermal battery through the system, and if you consider one cycle for one day, so it can last until 10 years of equivalent operation. And so that is, so, okay, come to the solar collectors applications. Okay, so this is experimental study we have done, our group has done. We applied the phase change materials and nano phase change materials to the solar photovoltaic thermal collectors. And first of all, let's understand what is this photovoltaic thermal collectors. Thermal and why it is important to, why it is necessary, why it is needed in the PV systems. The PV system, why it is needed, because the PV system, you know that they operate well under the standard test conditions. The standard test condition means when the temperature is 25 degrees centigrade, radiation is 1000 watt per meter square, air mass is 1.5. However, when you put these photovoltaic panels in the real outdoor condition, you will find out that as the time goes up, especially in the afternoon, what happens? You have the higher penetration of the solar energy. In the morning, you have less penetration of the solar energy. And again, in the evening, you have a less penetration of the solar energy. So there is a bell-like structure in the solar energy graph, if you see. So solar energy in the morning is here, in the afternoon goes higher and then goes down. So when the panel is put in the outdoor condition, it gets the maximum energy here. When it gets the maximum energy in the afternoon time, the temperature, ambient temperature also goes up. At that time, what happens? The temperature of the PV panel goes beyond 25. So it goes roughly around, sometimes it depends what is the season. Okay, what is the, if it is a, especially suppose if you talk about the UP, Uttar Pradesh, you talk about the Rajasthan, temperature may go roughly around 48, 50 degrees centigrades. So during the, so there is a temperature difference of 20 to 25 degrees centigrade. So the PV power output drops 0.4 to 0.65% per degree Celsius rise in the cell temperature. So you can imagine how much power output drops when there is a temperature of 25 or 50 degrees centigrade. So you need to get the proper mechanism where basically you can manage this temperature, you can manage the temperature close to 25 degrees centigrade so that you get the maximum power output. So you can do this utilizing different methods. One is you, if suppose you have the natural ventilation of the air, which is known as the passive cooling, or forced air or water or refrigerant, which is known as the active cooling. Okay, so so he means, but when you are having the especially the water, refrigerant in this, the problem is that this is active cooling. You need the pump to pump the water or refrigerant. Okay, so alternative, you can go for the phase change materials. You can directly apply to the phase change material to the panel. Okay, and you can improve the electrical energy, or you can apply the phase-change materials, as well as you can apply the thermal collector to it, and you can not only improve the electrical energy, but also you can get the thermal energy out of the PV collector itself. So PVT means photovoltaic thermal. This is a hybrid. With the PV, you attach the thermal collector into it to harness the thermal energy. So that is known as the photovoltaic thermal collectors. Okay, so this is one of the setup. This is the published study and also patented. So what we have done, we have attached the thermal collector into it in a particular arrangement of the thermal collectors, and we studied at different mass flow rate, and also in the next, what we have done, not only the water we have flown, but also we have attached the phase change materials to it. And further, we have, because when you are attaching the phase change materials, the thing is that you are ensuring the system's reliability. Means when you need the, suppose in the daytime, it is when you are attaching the thermal conductor, it is what it is doing. It is basically reducing the panel temperature, which may improve the electrical efficiency, but also you may get the thermal energy. But what happens in the night time? So you need the storage. So for that, what we have done, we have attached the phase change materials into it, and you can see the results. Okay, you see that this is the PV as a reference. So PV as a reference, you will find out the electrical efficiency was roughly around close to maximum 9.89%, and you do not have any thermal energy. But when you attach the thermal collector into it, the maximum efficiency goes as high as roughly around 10.39%, and further, on top of that, you get the thermal output out of the same system. You do not need another area. With the same area, you can get the thermal output as well as the enhanced electrical energy. Then further, what we have done, as shown in the previous setup, we have attached the phase change materials to the PVT collector. So you can see that the thermal efficiency was further improved from 74 to 87%, and also the electrical efficiency goes from 9.89 to roughly around 11.65. Of course, at different flow rate, whatever the flow rate, I don't want to discuss that one. I have some more results to discuss. That's why I'm not showing in detail. I'm not showing here what is the impact of mass flow rate actually. But at this mass flow rate, we got maximum electrical efficiency of 11.65, which is roughly from 9.89 to 11.65 is roughly around, you can say that 1.5% of the enhancement of electrical efficiency, as well as the thermal efficiency is roughly around 87%. So which is a quite good results. So we have not done this study only on kind of a PCM PVT, but also we have done a comparative study of the photovoltaic panel, photovoltaic thermal panel, photovoltaic thermal with phase change materials, then PV directly applied to the PCM, PV directly applied to the nano enhanced phase change material, which the results I was showing you, whether it has the impact when you go for the real life application or not. So that's very important. Sometimes, suppose the material is showing a good result in the lab scale, whether it is practically applicable or not. So we have done this study. You can see the results here. Average, this is the average electrical efficiency. If you see here, the PV at Kuala Lumpur we have done, and we have done this study from 0.5 liter per minute to the 4 liter per minute of this, and you can see that the average electrical efficiency was roughly around 5.5% here when PV alone, but when PVT collector is there, it goes more than 6% of the efficiency. And when we have attached the PCM into PVT, we find out that using the dual application, you will find out that it goes more than 6.5% of the average electrical efficiency. And when you attach the with PV with any PCM without thermal collector, the electrical efficiency is quite good, more than 7% of the average. But when you attach the nano enhanced phase change material with the PVT collector, you get the maximum electrical output, close to 8% of the average electrical efficiency. So with this, if you see with nano enhanced phase-change material to the PVT collector, if you are integrating, you are enhancing 5.5% average electrical efficiency to close to 8% of the electrical efficiency. How much is around 2.5% of the enhancement, and you know that in the solar panels, solar cells, even 1% of enhancement is quite good improvement in the electrical efficiency. So and on top of that, you know, electrical efficiency with these collectors, especially PVT, when there is, you get the thermal output as well. So overall, this is one of the very good system. So this left-hand side we have shown with the help of flow rate, and the right-hand side we are showing how it varies over the radiation. So thermal efficiency again, I won't go much into it. Maybe. Okay. So solar thermal, another solar thermal collector. What we have done this study. Recent work we have done the ETC based water heating system. We have used heat pipe into the, you might have seen this type of a solar water heaters on top of the roof. So basically what is the function in this? You'll find out that basically there will be a tank, and with the tank the water goes here, and this water goes basically in the pipes throughout this, and at the end you'll find out the hot water from here. And solar radiation falls basically on the surface of this solar thermal collectors, which is coated, and the radiation goes, and the basically there is a heat transfer from here to the water, and you get the hot water. Okay, but what we have done, we have not we have utilized the hollow space of UACT tube, and we inserted the heat pipe into these UACT tube collectors, and we flown the water through the heat pipes, and the remaining space means this is the remaining space, because now water is going through the heat pipe and we have a remaining space. We utilize this remaining space. We inserted the phase change materials into the remaining space. So what happens? You can get the flow of water through the UACT tube, through the heat pipe, and this space is filled by the phase change materials, and these phase change materials basically get charged when this water is basically flowing in the daytime. And we tested it out in the evening hours. Evening hours, you see in the test one, you can see that even in the evening hours, if you see here, the water what you are getting, even in the evening hour, means after 5 o'clock also you are getting around more than around 40 degrees centigrade of until 11 p.m. I means especially for water for bathing and small what you call the kitchen applications, you need such type of a water temperature. So still we tested until actually 6 a.m. 6:30 a.m. So the because of the phase change materials which is inserted into the tube, without acquiring any different other space, you can come out with the surety to supply the heated water not only in the daytime but also in the nighttime. So PCMs can be applied in the building thermal management as well. So we have done, as I told you, 1/3 of the need is around the building energy. So this is the map of different countries, what kind of temperatures are there, what is the cooling, and right hand side you can see there's the average temperature of country in degrees Celsius. So the red one is basically kind of between 20 to 25, and the blue one, when it goes blue, darker blue, is between 10 to 5 or 0 degrees centigrade. Black is showing where it is below 0 degree centigrade. So this mapping is important to understand what kind of a melting temperature of the basically phase change materials is needed. And left hand side you can see the average temperature in degree Fahrenheit. Okay, I won't go in detail how it works, but you can apply the PCMs in different applications. Different way. You can apply the PCMs on the roof. You can apply the PCMs in the walls. You can apply the PCMs in the window. You could be having the solar chimney. and you can basically cool the room in a passive way without utilizing the active system. And you can, I won't say that you are going to manage 24/7 utilizing the PCM, but especially the peak energy demand can be managed utilizing the heat stored in the PCM, whether it is a cool energy or it is a heat energy. So these are different methods of incorporating the PCMs into buildings. Okay, so this is one of the study we have done a long back. Basically, we came out with the PCM we applied here, kind of in the stacks, and these stacks were put in the, especially in the sides of what do you call this, telecom towers. So there we utilized, and there was a lot of need for the cool energy for the site. So we started using the calcium chloride hexahydrate we used, and in different ways in the panels and in the walls it was utilized. Okay, so yes, we have done a lot of study on this. Okay. Yeah, so that's all from my side, and if anyone would like to basically connect with me, they can connect through the LinkedIn. Basically, this is my LinkedIn link, and you have my number as well. That's all. Thank you very much, everyone,
Thank you,
and
sir,
I'm open for Q&A.
Thank you, sir, for very wonderful presentation.
Yeah.
Dr. Murli. Dr. Murli,
Yes, sir.
kindly share that first slide. Now, any question from participant side?
There is one hand raised. I can see JB and Mohan.
JV and yes, sir. And
You can open there, and I would like to answer.
Mohan man.
Yeah.
Hello.
Yes.
Good evening, sir.
Good evening.
Sir, I have only one question. Like,
Yes.
I attended your throughout the presentation, and also I read your articles. So, actually, as I seen in case of tetrapod engineered year one paper in CEJ.
Yeah.
So in that case, sir, the thermal conductivity has been increased, but the latent heat is remain constant. So I have one question, that is there any effect of certain geometry that can preserve the latent heat? That means I wish to know that is there any effect of certain geometry that will keep constant the latent heat, or it will suppress the reduction of latent heat?
Yes. So in terms of basically nanomaterials, the thing is that all sorts of nanomaterials having different shapes, different dimensions. So shapes, dimensions, these all basically works. But there means you cannot say that there should be a particular one shape that will suppress or will keep that latent heat constant. There is no answer for that. But it depends on the material to materials, and that is subjective to what kind of a material, what kind of a nanomaterials you are doing. But yes, there, what I can say that its shape basically works in suppressing or maintaining the latent heat. So in tetrapods, because of its unique size, the kind of a dimension it has, because of that, we were able to maintain the latent heat.
So, okay, sir. Thank you.
Yeah.
Any more question from participant side? Dr. Amar Kumar, JV. JV.
Hello.
JV.
Yes.
Hello,
Yes,
sir.
so-
Good evening. This is Dr.
Yes, yes.
Sir, I have a question related to this PCM, sir. Sir, I have gone through this entire sir, discussions. I just want to know, sir, whether we can use this PCM in different type of coatings so that we can preserve the heat and you can utilize it in for different type of applications related to the lighting and all.
Related to
Related to this electrification or lighting, particularly for the lighting purpose. Like we have
okay. So as far as coating, yes, you can do the PCM coatings. The PCM coatings can be lighting, means exactly for the lighting, you cannot come out with that for the PCM, but you can do the PCM coating on the buildings, in the walls, and you can do that in the external walls basically. And you have to not only the PCM, but also you have to infuse other kind of a nano coolant into it, so that it basically registers the solar energy, which is it can reflect, and also it can store some sort of energy. So I won't say that for the lighting, but for the reduction of the building temperature, you can utilize the PCM coating, and also the PCM coating can be utilized for in the textiles. Means that can be utilized.
okay, sir. Thank you.
You're welcome. Okay, so Dr. Abhishek.
Yes, sir. Any more question? Okay. Dr. Murli, can you remove the slide? And I request all the participants to switch on their camera so that we can take one group photograph with the Pandey sir.
Yeah.
Dr. Murli, kindly remove the presentation. I request all the participants kindly switch on the camera so that we can take one photograph with Pandey sir. Yes. Okay, sir. Thank you, sir, for wonderful presentation, and thank you for accepting our invitation. Thank you, sir.
Thanks, Dr. Abhishek.
Yes.
See you.
Yes, sir.
Take care.
We are closing this. Yes, sir. We are closing this meeting, and we will start the next session at 7:45.
Okay, Dr. Abhishek, I'm leaving. Okay.
Yes, sir. Thank you,
Thank
sir.
you.
Thank you. Thank you. So after 10 minutes of break, we will start next session.
Okay, sir. Thank you, sir.